everybody, it's Grip coming to you from the basement workshop, and I am going to weigh in on shot placement and deer anatomy today. Seems to be a pretty hot topic on the internet, and I'm going to throw my hat in the ring, and this is going to be a long one, so buckle up and get ready. For those of you who don't know what I do for a living, I'm a high school anatomy and physiology teacher. I'm in the middle of my 31st year in education, and I'm certified to teach the biological sciences, and I've taught general biology, and I did that for about 20 years. And I've taught human anatomy and physiology for 28, 29 years. I've taught zoology and a few other ologies that are out there on the biological umbrella, but that's what I do. So this, the idea started it was months ago, and I've been working on this for quite some time, but I was with the Mobile Hunter Expo team and was working the shows over the summer, and we were in our show in Kalamazoo, Michigan. And there I ran into a gentleman, had an interesting booth by the name of Brian Johnson. Not that Brian Johnson, but he has undertaken, which I think is a great idea, and he has undertaken the task of trying to educate all of us as bow hunters into the anatomy of a white-tailed deer. And his series is called The Anatomy Hunter. And he has done extensive research. He has some really cool models. I'll probably flash in some of the pictures and stuff that he has there. And we started a discussion. And he got very excited when he found out what I did for a living, and he grabbed his wife and had her video us, and he was asking me questions. We were talking about a few things, and he would ask me a few things, and I would answer to the best of my abilities. And he actually, I don't know if he knows, but he offended me a little bit because I answered one question, and he says, "How do you know all this stuff? You're just a high school teacher." And I had to take it kind of took me a little bit. It set me back a little bit. But, he says, "I've talked to doctors and so on, and they can't help me." And, well, I answer questions for a living. My students come to me with questions. You would not believe all the questions that they come to me. So I've been answering questions for 3 decades about the human body and how the human body works. And typically, if somebody asks me a question I don't know the answer to, I'll say, "That's a great question. I'm not real sure." And then I will go look it up. And then I'll keep that knowledge. I'll retain that information for the next time somebody asks me the same question. After a while, you answer the same question for 30 years, it starts to sink in, even for a big dummy like me, just a high school teacher. But that's how this all got started. And I thought, you know what? He's doing a great thing. I'm going to help him out. I'm going to go ahead and offer up what I have come to learn about the human body. And because we're both mammals, we're roughly the same size, I think that there are a lot of similarities when it comes to our anatomy and how our bodies work. So this is going to be a long video. If you didn't look at the time and you clicked it, and you thought, oh, well, let's check this out. And you're one of those short attention span people who, you can't hang on for more than about 3 or 4 minutes on a video. The TikTok people who only like 30-second videos because that's as long as their attention span is. This video is not going to be for you. Once I get started on this is going to go a while. So make some popcorn, sit back, grab a drink, relax, and maybe sit back and you might learn something. So one of the questions that I ask myself, or that I don't know if anybody else has ever asked, but we as bow hunters have always been taught that the shot we want to take is the double lung. And I'm not saying that is bad or poor information. Anybody that's ever double lunged a deer probably realizes it's very lethal. But you have to look at the history of bow hunting. You look back at the grandfathers of bow hunting. You got Jim Dartery and Fred Bear and Howard Hill and those guys. They were all shooting stick bows, recurves. Their range is, anybody that's ever shot those bows and has shot compounds, compounds are a little easier to master, to be accurate at longer range. That's why they're so popular. So those guys are wanting the most bang for the buck. They want the organ that is going to have the highest concentration of blood vessels. Because let's not kid ourselves. We're talking about the cardiovascular system. When if you talk about cutting diameter and you talk about blood and blood trails and bleeding, then you're talking about the cardiovascular system. We operate on a closed circulatory system, which means blood stays in our blood vessels all the time. When it comes out, you're bleeding. That's where that comes from. We don't have an open circulatory system. So it's all about the blood loss. And if it's all about blood loss, then we're talking about the cardiovascular system. So we're looking at this you have to realize we're going about this in two different ways. Are you shooting the deer to directly take out the cardiovascular system, or are you shooting the deer to take out the cardiovascular system by taking out the lungs? Yes, you are handicapping their ability to breathe, but we have all heard stories of deer that were hit on one lung and lived. Why and how that is, I don't know. They're tough. They don't dwell on it. When they get shot, they don't say to themselves, "Oh, that's my liver." They just go, "Well, that doesn't feel right. Oh well, I got to go on with life," and they just go on. They don't know enough to know what's happened to them. But again, it's all about the blood loss. And without getting down the rabbit hole of broadhead choices and your arrow weights and getting into the heavy arrow, light arrow, expandable, fixed blade, whatever. In my humble opinion, arguing over which is the best arrow system to use is kind of a waste of time. I think it's better to arm ourselves with knowledge and then pick the arrow system that's going to work best for you. If you've got an arrow system and a setup that works for you, great, use it. I don't care if it's an expandable on a light arrow. I don't care if it's a heavy arrow with a cut on contact and a fixed bladed head, single bevel, double bevel, a hybrid broadhead. Man, if it works for you, great. To me, I think it's something I teach in zoology that's called coevolution, where nature has solved a problem from two different standpoints. And the classic example is flight. Birds fly, butterflies fly. They go about it in two separate ways. The butterfly wing is an extension of the exoskeleton, still allows that animal to fly, along with grasshoppers and beetles and all the flying insects. Those wings are extension of the exoskeleton. They work. Those animals fly. A bird, that is an appendage, that is a limb, and it's covered with feathers. Birds, they're able to fly using a different body part that still does the same job. And then you want to throw in the wing of a bat. That's also an appendage, also in a limb, but it's covered with skin. So does it allow the bat to fly? Yeah, very well. And they don't argue over which way is to fly. What's the best way to fly? Because they all can do it. So if you've got an arrow system that works for you, that's great. I really don't want to get into the argument over that. What I want to talk about is, what are these arrows doing to the deer? And if your aim is to take out the cardiovascular system directly by shooting at and trying to take out the heart or cut the top of the heart and sever those very large blood vessels, then you're probably going to lean to a specific arrow system because of the problems that you can run into by shooting at that area. If all you want to do is take out the cardiovascular system by running a big, large blade through the lungs, and you don't care about shooting for the heart, but double lung is your goal, then maybe you're looking at something else. Both of them put down whitetail. I will say, though, that both are going to have their pros and cons. It's a give and take, and it really all depends on what you want and what you're doing. Again, I really don't want to get into that argument over which one is best. I really don't think there is a best. There might be a best for a particular frame of mind, but if I'm shooting for the heart and I'm holding tight to that shoulder, I don't want a 375 grain arrow with a 2-inch expandable. I'm going to look at something else. So all I really want to talk about is just the anatomy of it. Okay, so with all that being said, let's jump into the first little video break that I have planned, and that's going to be me talking over some illustrations that I use in my anatomy classes. In the respiratory, the unit on the respiratory system that I teach, and the unit on the cardiovascular system. I'm going to go into capture images from the PowerPoint that the publisher of the textbook we use have given me rights to use in class. So hopefully we'll go into this and we'll come out on the other side having learned something, because that's what I do for a living. Okay, so this first one, this is basically a very simplified map of the blood vessels in the body, the arteries and veins, and where in the body you're pumping oxygen-rich blood and where oxygen-poor blood can be found, and the pathway that they take through the body. I call it the figure 8. And when you look at this diagram, you'll probably see the connection. So let's go ahead and jump into that.
All right, so quickly here, let's take a look at the map of blood flow through our cardiovascular system. And again, we're mammals, so we have a 4-chambered heart. And some of the mapping here will be a little bit different. The digestive system for a whitetail is a little different than the human, but we get the idea. Our 4-chambered heart is basically 2 pumps in one. Now, for reference reasons and for ease of recognition, almost all texts and references when we're dealing with oxygen poor blood, they always color those sections of the diagram blue. So in any area we see is our key here says deoxygenated. I typically call this oxygen poor. Anywhere that's blue is going to be the section of our cardiovascular system that is carrying oxygen poor blood, and anywhere that is red will be oxygen rich. Now, hopefully we all realize there's no such thing as blue blood. It's just colored this way for ease of reference and recognition. So I refer to this as kind of a figure eight. The right side of the heart is known as the pulmonary pump. Its job is to pump oxygen poor blood to the lungs for reoxygenation. So regardless of where we start, we'll just start in our path through this system. We'll just assume that we'll be an oxygen poor blood cell in either of these large veins here. So we'll talk veins and arteries. The difference: veins always bring blood back to the heart. Arteries always carry blood away. A lot of my students, when I ask what the difference is, one of the things that they will say is that all arteries carry oxygen-rich blood and all veins carry oxygen-poor blood. And for the most part, that is true, but there are a few exceptions to the rule, and we're going to talk about those here in just a second. So starting here at the vena cavas, for the human, we're upright, so we refer to these as the superior and the inferior vena cava. But for a whitetail, because they are quadrupeds, down on all fours, this is going to be front and back. So in a deer, this blood vessel will be the anterior vena cava, and this is going to be the posterior vena cava, bringing blood from the back half of the body back up to the heart, and the anterior will be bringing blood from the front of the body back to the heart. So all of this blood is going to be oxygen poor. So it's been used up, it's dropped off its oxygen at the tissues, and it's making its way back to the heart. So through one of the vena cavas, it's going to empty into the right atrium. Right atrium will contract, send it to the right ventricle. Right ventricle contracts and sends it up this rather large artery. So here's a blue oxygen poor carrying artery, carrying blood that's oxygen poor. It's called the pulmonary trunk, and it will fork into the right and left. You can see right here, this fork. It's going to fork into the right and left pulmonary arteries. So the right pulmonary artery is going to take oxygen poor blood to the right lung. The left pulmonary artery is going to take to the left lung. And here in the lungs, this blood is going to be reoxygenated. As we can see, it goes from blue to red, and it's going to come back through these pulmonary veins. So here we have a network of veins carrying oxygen-rich blood, and there'll be two more coming from the right. We can't see them because they're behind all of this, but they're going to come in here, and they are going to empty their contents of oxygen-rich blood into the left atrium. Left atrium will contract into the left ventricle. This side of the heart is known as the systemic pump because it is going to pump oxygen-rich blood to all of the body's systems. So again, the atrium sends blood, left atrium, sends blood to the left ventricle. Left ventricle contracts and sends blood up into the aorta. And this is called the aortic arch, or arch of the aorta. And from here, blood can go anywhere and will go anywhere into the body. So if we come up this way, this blood is going up to the top part, or for the deer would be the front part of the body. So it's going to supply blood, oxygen-rich blood to the brain, muscles of the neck, to the front leg, so on and so forth. And if it turns down and goes behind the heart, this would be known as the thoracic aorta. So it goes right along just underneath the spine, and it's going to follow all the way down. It will supply oxygen-rich blood to the visceral mass, all of the organs of digestion, and it will make its way down to the pelvis, where it will fork at the common iliac and go through the pelvis, and then it will eventually supply blood to the hind legs. And then we see all of these capillaries here. We see the red blood is changing into blue, indicating it is now oxygen poor, and it's going to make its way back through all of these veins. It's going to make its way back into the vena cava, and it will then complete its figure 8 lap. All right, so in review, real fast. So we go from the vena cavas into the pulmonary pump, the right side of the heart, out to the lungs. Blood is reoxygenated, comes back to the heart, the left side, the systemic pump, and then this side of the heart will pump it to anywhere and everywhere in the body, including back to the lungs, because the lungs need oxygen as well. They're a tissue, they're an organ that needs oxygen-rich blood, just like all of the other parts of the body. So there is a double set, as we talked about earlier, there's a double set of blood vessels that are going to be bringing blood to the lungs. The first set is bringing oxygen-poor blood to be reoxygenated, and the second set, we call that the pulmonary blood vessels, and then the bronchial blood vessels will be bringing oxygen-rich blood back to the lungs to provide that tissue with oxygen-rich blood. So that's why the lungs are such a valuable target, because of their density of blood vessels inside that tissue.
Okay, so that's the path of the blood flow. Now let's look at the organ that is the pump for all of that blood. And in this next slide from the PowerPoint, it has a artistic rendition of the heart and the blood vessels, and a picture of a real human heart from a cadaver, and has them side by side and labeled. And let's talk about the heart and its makeup.
All right, let's just take a real close look at the heart. This is, again, human heart. I've been a part of, I don't know how many hundreds of sheep heart dissections that I have done in my anatomy classes. And I can tell you we use sheep hearts because they are virtually identical structurally to the human heart. And they're roughly the same size. And I have had quite a few deer hearts in my hands as well. And they look just like the sheep hearts, and the sheep hearts look just like the human hearts. So our makeup is the same. But one of the things I want to point out here, I'm going to turn my pen on again, is we see the blue side, that's oxygen poor. Okay, it comes in. This is the real thing. They have done us the favor of coloring these coronary blood vessels. These are the blood vessels that are responsible for supplying the heart muscle with its oxygen-rich blood as well. And you can see in this diagram here, they come off the aorta very soon. As soon as that blood hits the aorta, it's important. You got to supply that heart muscle with oxygen-rich blood. They peel off, these coronary arteries peel off, and they come down here and they supply the heart muscle. These that are faint we're kind of looking through the heart. They're on the back, or what we would call the posterior side of the heart. And these that are more vividly colored are on the anterior side, the front of the heart. And so you may know that if you get one of these blocked, that's a heart attack. That's anything downstream of that coronary artery is going to be denied oxygen-rich blood, and that muscle doesn't like that, and so that's what we call a heart attack. And we can see again, they've colored them neatly for us. So this is a coronary artery, and this is a coronary vein. So it is going to take oxygen-poor blood back, and it's going to empty it into the right atrium in what's called the coronary sinus. And that is going to be right in the back of that right atrium, right there real close to the superior and inferior vena cava, where they enter and empty their oxygen-poor blood into the right atrium. And these are very important. They peel off the aorta very quickly. And you can see here in this heart, this is the aorta. This big blood vessel right here is the aorta. And I was talking about these earlier on the different arteries. You've got brachiocephalic, and that's going to fork up here into the subclavian. The right subclavian is going to go into the clavicle, and this is going to be the right carotid artery. This is going to be the left carotid artery. I don't know why there's no brachiocephalic on this side, but there's not. And then this guy is going to be the left subclavian. It's going to go up underneath the clavicle. So you can see there's a lot of big arteries that come off of this even bigger artery. And so a broadhead that comes in and cuts these, that's lights out. That means you cut these, that's going to be both of the blood vessels of the arteries that are going to be supplying the brain with oxygen. And that, to quote a student of mine, that does not equal good for the deer. Good for us, bad for the deer.
Okay, now that we've talked about the blood vessels and the heart, let's switch gears and let's go talk about the pulmonary component of our target. The heart is situated, as we mentioned in that past slide, in a space called the mediastinum. And to get to the heart, unless the deer stands up and you're able to put an arrow straight through the sternum as if it were walking upright, you're going to hit lungs. You cannot get to the heart without hitting lungs. So, and we've been told time and time again, double lung, double lung, double lung. So let's talk about why the lungs are so valuable, and let's look at their anatomy.
All right, so first I wanted to show this picture. This is from the PowerPoint that came with the textbook that I use at school. And this is a picture of the upper torso of a cadaver. And so we can see this blue line. This is up here on the top left. This is the plane that this cut was made. And then we are looking at as you can see here, the view is from the diaphragm up. So we have taken this, basically the bust of this cadaver, and laid it flat. And so now we are looking upwards into the chest cavity. So the heart has been removed. Just to give you some reference, this is the arm. So the shoulder is going to be up here. This is all the chest cavity, the thoracic cavity. We can see the sternum. These are some of the muscles in the back. Here's the vertebrae and the spinal column. So a couple of things that I wanted to address in this picture is, number one, the lungs are not a balloon. If I hear one more internet personality say we as bow hunters need to pop the lungs like a balloon, I'm going to lose my fecal matter. Take a look at this organ. It is not a balloon. It's a sponge. If we're ever going to see a lung deflate like a balloon, this one has been cut in half. So clearly, it would deflate and fold flat, and that's not what really happens. You can see it still occupies a major portion of this thoracic cavity. So that's the first point I wanted to make. The lungs are not a balloon. Secondly, this would be above the heart, and we can see there are a lot of very large blood vessels in this area. This is called the mediastinum. This is the space in between the lungs that's going to be occupied by the heart and these large blood vessels. The esophagus comes through there. Now, this cut has been made just below where the trachea has forked, and so we're just below where the primary bronchial tubes, and this is going to be one right here, and this is another, as that primary bronchial tube is branching and forking into the lungs. So this artery, the aorta, this is the trunk of the systemic arterial tree. All oxygen-rich blood that's going somewhere is going to have to come through this aorta. This is the superior vena cava. This is returning oxygen-poor blood back from all parts of the body. So this is that first thing I wanted to discuss was how much the lung is not a balloon. It is a sponge, and it is full of blood vessels, capillaries, both pulmonary and bronchial blood vessels, and we'll talk about them here in a little bit. The other point I wanted to make was the dead space that a lot of bow hunters believe exists inside the thoracic cavity. They believe that an arrow can go through the space between the thoracic cavity and the lung, just under the spine, and not damage any of the lung tissue. Two things I want to point out that doesn't happen. The lungs occupy the overwhelming majority of the thoracic cavity. This lining, which is called the parietal pleura, secretes a liquid, a fluid, as a component of the lymphatic system to help lubricate and keep this surface moist. And the body drains that fluid to help maintain a negative pressure outside of the lungs in this pleural space. And as the body drains that lymph fluid, it keeps an air pressure below atmospheric pressure outside of the lungs. Not only does the fluid do that, but the fluid also will have a tendency to, due to cohesion, will want the lining of the outside of the lungs, called the visceral pleura. It'll attract that lining, and due to cohesion, will want to keep that lung touching the surface. So that way, as the chest is expanding and contracting, that lung will have a tendency to go with it. And those reasons are why that space simply does not exist. A lot of times people don't realize how low the spinal column goes, and you're basically shooting them through the backstrap and going through a part of the vertebrae called the vertebral spine, which is the process that's going to stick up. And we'll look at that on one of the slides of a whitetail here in just a minute. All right, in this slide, we are looking at the lungs separately. You can see down here, this is medial view of the right lung, which means we are basically, this would, if we were in the mediastinum, right there in the heart, looking at the lung from the middle out, this is what we would see. And this is the left lung from a medial view, again from the middle looking out. We see here right in the middle, which is going to be basically, this is going to be coming off the top of the heart. We see the bronchial tubes, the forking of the bronchial tubes here and here. We see these large blue, so these are going to be carrying oxygen poor blood. And since they're going into the lungs for reoxygenation, these are going to be branches of the pulmonary arteries. That blood will then branch further from all of these into the capillary beds around the alveoli, and then come back into these. We'll head back to the heart through these red, the large red tubes. Those are going to be the pulmonary veins bringing oxygen-rich blood back to the heart. And we have the same thing over here, pulmonary arteries, pulmonary veins. So we understand how the arterial tree works. As these get further, as these blood vessels get further from this point, they're going to get smaller and smaller and smaller. So down here, you can see this cutaway. This is kind of a dome shape because the diaphragm is dome shaped. And so as when we are exhaling, the diaphragm is going to be way up in here. And when we take a breath, the diaphragm drops. And so it occupies this space. If you think three-dimensionally, we're kind of looking at the curve of the diaphragm. So there's very little lung tissue towards the lateral edge of the very bottom part, the base of the lungs out towards the side. Because the diaphragm is in here, this lung tissue is not very thick. And the further we get away from these, the smaller those arteries and veins are going to be. So here close to where they enter the lung, they're going to be larger, and or coming out of the lung and going into the lung, they're going to be larger here. But out here in the tips, these blood vessels are going to be a lot smaller because it's, just like the branches of a tree. You get out towards the end, the twigs are smaller than the forks and the trunk of the tree. It's the same principle. So while we're here, let's talk about the lungs. We mentioned on an earlier slide that, they're not balloons, they're a sponge. And the area of gas exchange in the lungs is called the alveoli. And this shows the alveoli. And the alveoli are a collection of tiny, microscopic, little bitty air sacs. So if you're going to use the balloon analogy, here's your balloons, but there's lots of them. They're microscopic. We can only assume that the numbers are going to translate from human to deer, but I can tell you the human lungs are going to contain roughly 300 million alveoli. That's a lot of tiny little balloons. There is simply no way a single broadhead, I don't care the cutting diameter, there's no way you're going to pop them all. The reason we have so many is that the body uses this strategy in a multitude of ways, but it is a question of surface area. Nature has figured out that it's more efficient to have a large number of tiny little things to get an incredible surface area than it is to have a smaller number of larger things. All right. For example, just to give you an idea, the amount of surface area the alveoli in the human lungs comes out to be about 750 square feet worth of surface area of alveoli for gas exchange. So every adult-sized human being walking around on planet Earth today has enough surface area of alveoli for gas exchange in their lungs to almost cover the entire floor of a racquetball court. A racquetball court is about 800 square feet, and most average adults are walking around with 750 square feet worth of membrane for gas exchange. The alveoli has that much. That's a lot. And since deer are roughly the same size, we can only assume that they are probably walking around with that much, if not more, surface area for gas exchange. So popping the balloon, again, is a misnomer. There's simply no way, because a broadhead only damages what it touches. It doesn't do what a bullet does. We're cutting tissue. And so deflating that lung, you're only damaging what the broadhead touches and everything that would be downstream of that. And you're just not going to get it all. It's just too vast.
All right. I know this is getting long, but before we go to my last PowerPoint slide, I have a question for you. We, as humans, the average human is walking around with about 8 pints of blood. If you had to break it down percentage wise, where do you think the blood at any given time, what's the breakdown uh, for the blood in your body? Is it going to be most of it is going to be in the arteries and because they're under pressure? So, the breakdown, is it going to be 50-50, half the blood in the arteries, half the blood in the veins? Or are you thinking, no, he's trying to trick us because there's going to be blood in the heart? So it's going to be about 46% artery, 46% vein, and the remaining percentage is what's in the heart, 8% in the heart, or what are we thinking? So comment below. There's a classic YouTube ploy. Comment below. Tell me what you think, where most of the blood is going to be found at any given time in the cardiovascular system.
So here's a percentage breakdown of the amount of blood that is in any given part of that figure 8 that we have. So hopefully on the question that I posed, you were honest and with your answer, but most people would justifiably assume that it's a figure 8. So at any given time, roughly half of the blood's going to be in all the arteries, and roughly half of the blood is going to be in all the veins. But as it works out, and again, this is for the human being, and we can only assume that this is the same for a whitetail, is at any given time, 64% of the blood in the body, we're talking about 8 pints, a gallon, give or take, worth of blood. Obviously, a larger whitetail is going to have a little bit more blood than a smaller. A year and a half old doe isn't going to be carrying the same volume of blood as a 5-year-old buck. It just kind of all depends on the individual, but roughly 8 pints worth of blood, or a gallon, is going to be in the body. 64% of that blood is going to be in the veins, the systemic veins. Most of this is going to be in a lot of the abdominal veins, and this acts as a reservoir for blood. So take a look at the other breakdown. At any given time, only 7% of the blood is going to be in the heart. As a comparison to the veins, at 64%, only 13% of the blood is going to be in the systemic arteries. So these are from aorta to the carotid arteries, the subclavians into the brachials, the femoral, all of those arteries that are carrying oxygen-rich blood at any given time, they're only going to hold about 13% of the blood. That's for anyone who has ever blood trailed a deer and has thought to themselves, how is this animal still bleeding? The reason is that the reservoir of blood in the veins, it's a pool of blood that is there for just such an emergency. As the animal bleeds, the body, due to vasoconstriction, can force blood from the reservoir and dump it into the system, push it up into that circulatory path to replace the arterial blood that has been lost, and that's just how the body functions. The capillaries, even though they are everywhere, but they're really, really narrow, so the volume of blood isn't going to be a whole lot because they're just not that big. Even though they're spread out everywhere, you're only going to come in at about 7%. The lungs, all the blood vessels in the lungs, pulmonary, so these are the blood vessels that are carrying blood that's going to be oxygenated, are only going to have 9%. And so I don't know what the breakdown is, but of the 13% of the systemic arteries, a small percentage of those are going to be going to the lungs as well. So if we're talking about all blood vessels, total blood vessels in the lungs are technically going to be a little bit higher than 9% due to the fact that they have, again, that double set of blood vessels. So this is just an interesting little tidbit of information about where and the breakup of blood is in the body.
Okay, pretty surprising. That's a. I think a lot of us, if you were honest, I think a lot of you out there, myself included, I remember seeing this graph years ago, and I had it had a few things dawn on me based on my experiences with running arrows through deer. And when you realize that such a large percentage of the blood is in those abdominal veins and the visceral mass, it answers a question. For example, actually, I was just talking to a friend of mine who shot a buck, and he said he wasn't sure where he hit. The arrow went through. He was shooting a large expandable. Arrow went through the deer. The buck ran off, and he stopped. And he said it looked like he was losing blood pressure and he was going to fall. And then all of a sudden, he kind of regained himself and took off. Well, that's vasoconstriction. That was after the initial shock and his body of the arrow running through him, and the buck's body realized that he started to lose blood and drop in blood pressure, and we started squeezing blood out of the abdomen and started pumping it into the system. And the lungs are unique. When they suffer trauma, they will constrict their blood vessels so that it limits their blood loss. That's kind of a unique thing. A lot of times there's trauma, the blood vessels will dilate so that we can get blood to that injured organ. The lungs are unique in that those blood vessels, when there's bleeding in the lungs, they will constrict, and so that they don't lose as much blood as fast. So that's, if you've ever had that happen, that's why. And something else, and I'm going to throw some pictures up here, but something else that I think, because they're not very well versed on the anatomy of a deer, and then I'm not talking about the organs, but I'm talking about the vascular tissue where these large blood vessels are in the body. My suspicion is that a lot of times what we are saying was a lethal double lung hit was aided by that broadhead not only hitting both lungs, but also severing those large blood vessels. So if we look at this picture, you can see that the posterior vena cava and the aorta is going to be right underneath the spine. The vena cava is going to be a little bit lower, especially while it's still in the chest cavity area. Someone was commenting on a tactic that they use when shooting at deer at longer ranges, is he shoots for the middle and he's hoping for high lung. And my theory is the reason that back high lung can be lethal is because of the posterior vena cava. You sever that large vein, and all of the blood from the back half of the body, from that cut in the back half of the body, is trying to get to the heart. So all the blood from the legs and all of the visceral mass, that blood, especially if we go back to the pool of blood, the body is going to try to push that blood up into the system, and it can't get to the heart because the vena cava has been cut. And that's why I think when people field dress the deer, they see the hit in the lung, but do they look for the vena cava to see if it's cut? And would they even know the vena cava if they saw it? You got all that blood all over the place and your organs are flopping around all over. It can be difficult to identify what's in there. My educated guess is that back high lung hit is a lot of times you're causing damage to the vena cava and possibly the aorta, because it's going to be right there underneath the spine. When you cut both of them, it's a done deal. All right, guys. So I hope that was educational. I hope you made it to the end. I know it's pretty long. And most importantly, I hope that you were able to take something from this video, learn a little bit about the whitetail anatomy and how to best use your equipment to cleanly and quickly harvest these animals. We owe them that much. So as always, everybody, thanks for tuning in and watching me ramble on here on Grips Archery. I really appreciate it. Man, if you've made it this far, you're my kind of subscriber. So please, if you have not already, click like and subscribe and join the list. I'm hoping that if you made it this far, you're really wanting to learn and be a more lethal bow hunter, because quite frankly, that's what it's all about. Understanding how these animals work and the best way with your equipment to cleanly and quickly and humanely dispatch these animals. So if you know somebody who also could benefit from the video, share it with them, send them the link, and impart some knowledge and wisdom upon them. So again, thanks for watching, guys, and I'll talk to you later.